Hello students! Hopefully this is working. So, as announced in class, this Friday I won't be there to give lecture. The TA for the class will. So as a consequence, I'm going to be putting up a sequence of little mini video lectures which will explore the ideas that, well, otherwise we would do in class on Friday. So, let's begin. I'm, in fact, recording this Tuesday, but nonetheless, I have a pretty good idea what I want to talk about tomorrow. So let me state the result, which happened tomorrow for me, but 2 days ago for you. More precisely, we stated the full complement of axioms that govern the real numbers. The real numbers are a complete, ordered field. And we already said most of the properties here. A field is someplace where you can add, subtract, multiply, and divide. And there's a long list of axioms that govern that bit of algebra. An ordered field is a field in which there's a sense of inequality. A complete ordered field, well, complete means the following. An ordered, you might be seeing a cat in frame in a moment. An ordered field is, oh, there's a cat. Yes, hello cat. Can you get out of the way? Here, let's move you. Yeah, you can go up. There you go. An ordered field is complete, that was Oreo, if every non-empty set which has an upper bound has a supremum, which, if you like the more descriptive name for a supremum, is a least upper bound. And one thing that we saw in class, I'm not sure if we actually proved it, if you replace the word upper here with lower, then instead it has an infimum, a greatest lower bound. So let's get some mileage out of that. Let's prove something about complete ordered fields. We are going to prove Archimedes' principle, which says that the natural numbers, as a subset of the real numbers, are unbounded. So let's just think about this intuitively. All this is saying is, well, the natural numbers are unbounded means the natural numbers don't have an upper bound. There's not a real number that's bigger than every natural number. And that seems totally obvious. However, it turns out to not be the case for an arbitrary ordered field. There exist ordered fields, so that when you consider the natural numbers as a subset of them, they're bounded above. And that example, well, maybe I'll make a little extra credit in which you explore an example where that happens. But let's prove it. It'll actually be pretty quick. Claim the natural numbers as a subset of R have no upper bound. Well, let's proceed by contradiction. Suppose for the sake of contradiction that the natural numbers are bounded above. Right, because we're trying to show they have no upper bound. Let's suppose they do have an upper bound. The natural numbers do have a lower bound, 1. By completeness, then, the natural numbers, they're not empty. 1 is a natural number. If they have an upper bound, then they have a supremum. They have a least upper bound. Let's call it S. S for supremum. Is it possible, then, that S minus 1 is an upper bound? Well, Of course not. S minus 1 is less than S, but what does it mean to be the supremum? Supremum is the least upper bound, which means that every upper bound U for n satisfies S is less than or equal to U. So this doesn't satisfy the property that's at least as big as S, so it can't be an upper bound. So that means S minus 1 is not an upper bound for n. So there exists some element n in the natural numbers, so that S minus 1 is less than n. Aha! So let's see. We haven't contradicted anything yet. But let's see, if you want to see that n is a natural number bigger than S minus 1, how would you want to construct a natural number which is bigger than S? Well, of course, you just add 1 to both sides. n plus 1 is now bigger than, well, let's see, S minus 1 plus 1. Well, but that's the same as S. So let's I claim that this is the contradiction. Let's see why. Is n plus 1 a natural number? Well, sure. N plus 1 is in the natural numbers because n is closed under addition. The sum of any two natural numbers is still a natural number. But wait, then S isn't an upper bound. We've constructed a natural number which is bigger than S. So S isn't even an upper bound. But we assume that S was the supremum. The supremum, the least upper bound, is an upper bound. So there's a contradiction. So there's the proof of theorem in this set of notes, 1.6.1. The natural numbers have no upper bound. And hopefully that felt pretty good. The proof itself I don't think is so hard, but that's kind of a cool result, that you can do it out of the axioms we have. So here's how this is going to go. I'm about to hit stop, completing this video. I don't know anything about video editing. I'm going to start recording again, and there will be a second video that'll follow this exactly, in which I will begin proving, well, a not terribly surprising result either. The integers are neither bounded above nor bounded below. And what I'll encourage you to do is, the proof isn't so hard to fill the blanks in. So maybe actually, yeah, that's a good idea. I think I just won't fill this in at all. The TA will on an office hour in class. I'll say, fill this in. If you couldn't, then bring that question up if there's something that doesn't make sense in there. I'm going to hit stop. I will hit record again in a moment, but you won't know that.